Courses in the cement industry. Present to you. In this course, we will discuss coal preparation, fuels in the cement industry. In physical state, fuels classified as solid, liquid, or gaseous. The solid fuels consists of 1. Coal, anthracite. 2. Lignite. 3. Peat. 4. Wood. 5. Coke. Coal, lignite. This used in cement rotary kilns. Coke. This used in cement shaft kilns. Also heavy oil, and natural gas. This used as a fuel in the cement industry. The consumption of fuel in a cement plant. A. Dry process. 1. 83%, rotary kiln operation. 2. 14%, raw material drying. 3. 3%, coal drying. B. Wet process. 1. 96%, rotary kiln operation. 2. 4%, coal drying. Historical background. 1. In the 1890, pulverized coal firing achieved in the cement industry, in the USA. 2. Fuel oil and natural gas have replaced coal. For economic reasons in Germany, coal in total fuel consumption was 2%, in 1973 and increased to 6%, in 1975. 3. The investment cost of coal mines is roughly 20 times higher than oil or gas. 4. The exploitation cost of natural gas is 3 to 5 times lower than oil or gas. 5. Gas does not require elaborate transportation, and the construction cost of pipelines is only a fraction of the costs of railroads for the transportation of coal. 6. The cost of the coal preparation department of a cement plant is about 15 to 20% of the cost of total plant machinery. 7. When switching from coal to natural gas, in existing plant production costs lower by 8 to 10%. 8. Practically fuel oil and gas is ash-free, so the chemical composition of raw mix is free of variation due to the different ash content of coal. Coal formation. Introduction. 1. The majority of fossils recovered in Cape Breton can be traced to coal areas or coal fields. 2. Fossils have been found ranging from whole or partial tree trunks and branches to shrubs and vine growth. 3. Evolution dates back to prehistoric times, to approximately 325 million years ago, when the region was covered in lush, dense vegetation. 4. Coal beds consist of altered plant remains. 5. When forested swamps died, they sank below the water, and began the process of coal formation. 7. However, more than a heavy growth of vegetation is needed for the formation of coal. 8. The debris must be buried, compressed, and protected from erosion. 9. Even though all the biological, geographic, and climatic factors may be favorable, coal could not be formed unless the plant debris was submerged and buried by sediments. 10. There are 4 stages in coal formation: peat, lignite, bituminous and anthracite. 11. The stage depends upon the conditions to which the plant remains are subjected after they were buried. The greater the pressure and heat, the higher the rank of coal. 12. Higher ranking coal is denser, and contains less moisture and gases, and has a higher heat value than lower ranking coal. Peat, Stage 1. 1. Peat is the first stage in the formation of coal. 2. Normally, vegetable matter is oxidized to water and carbon dioxide. 3. However, if plant material accumulates underwater, oxygen is not present, and so only partial decomposition occurs. 4. This incomplete destruction leads to the accumulation of an organic substance called peat. 5. Peat is a fibrous, soft, spongy substance in which plant remains are easily recognizable. 6. It contains a large amount of water, and must be dried before use. 7. Therefore, it is seldom used as a source of heat. Peat burns with a long flame and considerable smoke. Lignite, Stage 2. 1. Lignite. The second stage is formed when peat is subjected to increased vertical pressure from accumulating sediments. 2. Lignite is dark brown in color and, like peat, contains traces of plants. 3. It is found in many places, but is used only when more efficient fuel is not available. 4. It crumbles easily, and should not be shipped or handled before use. Bituminous coal, Stage 3. 1. Bituminous coal is the third stage. 2. Added pressure has made it compact, and virtually all traces of plant life have disappeared. 3. Also known as soft coal, bituminous coal is the type found in Cape Breton, and is our most abundant fuel. 4. It is used in industry as a source of heat energy. Anthracite, Stage 4. 1. Anthracite, the fourth stage in coal formation, is also known as hard coal, because it is hard and has a high luster. 2. It appears to have been formed as a result of combined pressure and high temperature. 3. Anthracite burns with a short flame and little smoke. Mill types. Ball mill, or roller mill. The operating principles of these two types of mill differ in the following ways. A. 1. A roller mill requires more air to convey the material than does a ball mill. 2. This means that only part of the air from a roller mill can be used as primary air for a rotary kiln of the modern high economy type, as the amount of primary air would be too great in relation to rotary kiln combustion requirements, thus increasing heat consumption. 3. All or some of the air from a roller mill must therefore be dedusted in a separate filter. 4. If the raw coal has a low or moderate moisture content, the amount of air from a ball mill is generally no greater than can be used as primary air in the rotary kiln. We follow together mill types. B. Grinding plants with roller mills take up less space and have a lower specific energy consumption than ball mill plants, the power saving being 15 to 25% for the whole grinding plant. C. The feed to ball mills must be pre-crushed to approximate 25 mm lump size, and the drying capacity is limited to a reduction in moisture content of 12 to 15%, whereas a roller mill will handle material of up to 85 mm feed size, depending on mill dimensions, and remove up to 20% moisture. D. Roller mills are more flexible than ball mills, since the roller mill can easily be adjusted to varying throughputs within a range of approximate 0.40 to 100% of nominal capacity as required. E. Ball mills are usually preferred for grinding highly abrasive types of coal. Grinding. 1. Coal contains varying quantities of volatiles, both combustible and non-combustible. 2. All types of coal also contain hygroscopic, inherent, moisture as well as varying quantities of impurities, which are released in the form of ash in the combustion process. 3. The degree of grinding required depends on the type of coal used. Coal with a low volatile content requires a high ignition temperature and must be finely ground. Coal with a high volatile content, however, must not be ground too fine, otherwise, the volatiles will be expelled too quickly to be able to mix properly with the combustion air. Drying and air circulation. There are three factors that are decisive in determining the amount of air to be drawn through a coal mill. 1. The amount of air at a given temperature must be sufficient to ensure effective drying of the moist coal. 2. The amount of air must be adequate in relation to the evaporated moisture so that the dew point of the air leaving the mill is maintained at a suitably low level. In practice, the dew point must be 15 to 208 degrees C, lower than the mill exit air temperature, to prevent condensation in the ducts and the dedusting installation after the mill. We follow together. Drying and air circulation. 3. In air-swept mills, of both the ball and roller types, the air velocity must be high enough to extract the ground material from the mill. When specifying the moisture of coal, a distinction is made between surface moisture, which evaporates at ambient temperature, and hygroscopic moisture, which is more closely bound to the coal. We follow together. Drying and air circulation. The inherent moisture content depends on the geological age of the coal, with the moisture ranging from 1 to 2% in anthracite, to 10 to 20% in lignite. The amount of air to be extracted from the grinding plant, including false air and water vapor, will in this case be less than 1.5 kilograms air per kilograms coal, corresponding to approximate 17% of the combustion air, based on coal with a calorific value. Safe handling of coal. 1. The coal must be sufficiently dry for grinding, storing, and feeding purposes. 2. Excessive drying should be avoided, due to the accelerating process of oxidation, which occurs as the moisture content is reduced, with the consequent risk of spontaneous ignition. 3. In practice, drying off the small part of the hygroscopic moisture will ensure a high degree of safety combined with good processing and handling properties. Direct firing. 1. Implies a simple and cheap installation. 2. Regulation of firing in the rotary kiln is effected by varying the feed to the coal mill. 3. The coal meal produced is precipitated in a cyclone, and after passing an air sluice, it is blown into the rotary kiln. 4. Rotary kiln and mill operation are interdependent with direct firing, which means that mill throughput must correspond to rotary kiln requirements. We follow together. Direct firing. 5. Is the most commonly applied method of firing a rotary kiln. 6. After precipitation in a cyclone, the coal meal is stored in a bin, from which the burner is fed. 7. With indirect firing, the mill throughput is kept constant irrespective of rotary kiln output fluctuations, and short interruptions of mill operation do not affect rotary kiln operation, so long as there is an adequate supply of coal meal in the bin. Important note. In both systems, depending on mill and rotary kiln type, all or part of the drying air may be used as primary air in the rotary kiln, provided it is passed through a cyclone to remove most of the coal meal. Drying with inert rotary kiln gases. 1. Plants using inert rotary kiln gases, with an oxygen content of about 4% for drying and transport of coal, are becoming more commonplace. 2. They have the advantage that the risk of fires and explosions is reduced considerably when the oxygen level is kept below 14%. 3. Operating conditions and plant maintenance must be such that this limit is not exceeded during operation. 4. This is effectively controlled by an 2 meter, placed at dedusting installation outlet. We follow together. Drying with inert rotary kiln gases. 5. In an inert coal grinding plant, the temperature of the drying gas can to some extent be reduced either by adding cold, atmospheric air or by recirculating the mill exit air. 6. The dew point of the exit gas, when using cold atmospheric air, is lower than when using recirculation air. 7. In order to ensure efficient material transport, the airflow rate through the system must be maintained within a certain range. 8. It may therefore prove necessary to inject water into the mill to keep the system inert while operating with coal with a low moisture content. Dedusting installation. 1. When all the air passed through the mill cannot be utilized as primary air for rotary kiln firing, an electrostatic precipitator or a bag filter must be installed to dedust the air. 2. An electrostatic precipitator must be preceded by a cyclone for collecting most of the coal meal so as to reduce the average dust concentration in the precipitator to a level at which explosions do not occur. Safe operation. 1. Electric calorifier for preheating the precipitator to ensure even heat distribution during startup. 2. Electric heating elements with thermostatic control to prevent condensation during operation. 3. Vibrators for bottom hoppers. 4. CO monitoring device. 5. Thermal monitoring. 6. CO2 or N2 injection equipment for precipitator inertization. Rotary drum coal drying technology and plant design. 1. Coal, wet basis, from a coal storage yard or coal mine is loaded into a belt conveyor and conveyed to the ceiling feeder for a direct fed into the saving drum dryer. 2. After undergoing a process of medium heat exchange drying, coal is loaded into discharging conveyor belt from the discharging box, then the coal is conveyed to the storage yard. Note: hot medium, hot fuel gas, for coal drying is produced and prepared in a coal-fired hot blast heater. 3. After undergoing, the coal is loaded into discharging conveyor belt from the discharging box, then the coal is conveyed to the storage yard. 4. Hot medium, hot fuel gas, for coal drying is produced and prepared in a coal-fired hot blast heater. 5. The environment air, which is sucked into the flue pipe with an air blower, and hot fuel gas from the hot blast furnace, is sent to the drum dryer after temperature adjustment, where it heats the wet coal, and absorbs the water vapor. 6. The mixture of hot gas and water vapor goes through discharging box and flue pipe and is sent to the dust collection cyclone, for powdered coal recovery. 7. The preliminary purified gas is sent to the bag filter for further purification. 8. Then the waste gas goes through the exhaust funnel, and is discharged to the atmosphere by the induced draft fan. 9. The powdered coal collected by the first stage dust collector is loaded onto discharging conveyor by discharging spiral, and sealed coal discharger then mix with the dried coal. 10. The powder coal collected from the second stage bag filter is loaded into discharging conveyor by discharging spiral. In this diagram, we see drying system process flow. In this diagram, we see system principle of drying process. In this figure, we see the dried coal. See this video about the dried coal.
This system is centered around an 8 by 40 foot rotary dryer. It's a combustion chamber, refractory lined, approximately 16 million BTUs of available heat. That burner flame is surrounded by an auxiliary air manifold with an approximately 20,000 CFM auxiliary air blower. alongside that combustion chamber. Screw conveyor for feeding into the system, and the screw conveyor will be fed by customers' feed conveyors. This particular conveyor is a 4-foot wide flat belt conveyor for discharge from walking floor type trailers. Rotary dryer is turned by 3-phase electric motors. As the product dries, it goes down the dryer, goes to a discharge knockout box. Discharge on the knockout box is through a counterweighted gravity operated flap gate, which discharges onto bagging system or conveying to further processing. Knockout box has access door for maintenance and cleaning. Vapors are pulled through the knockout box, a labyrinth plates for knocking down particulate. Vapor continues through ductwork into a cyclone, and it's drawn through that cyclone by an approximately 34,000 CFM blower. Materials collected in the cyclone are discharged through this rotary airlock. Controls for the unit are in this 3-door panel. 120 volt exterior controls, start stops for the motors. We also have variable drives on the blowers and the drum. And on this particular model, on the feed conveyor, potentiometer is mounted on the outside of the door, so operators don't have to access the VFDs inside. And we also have 3 temperature controllers here. On the inside of this panel, variable drives, burner controller, line reactors for the variable drives. Now we'll fire the burner.
In this figure, we see coal after drying. Drum coal drying system. 1. The drying machine is a rotary metal drum, which is set at an angle about 3 to 5 degree, and rotates at a speed of 3 to 8 revolutions per minute. 2. The coal remains in the drum for 8 to 12 minutes. 3. The coal drum dryer are uniflow, which mean the hot fuel gas and coal are fed in one end and discharged at the other. 4. The heat exchange takes place during the process of gas solids concurrent flow in the drum. Divided into 1. A. The process is simple, and operation reliable. B. The factory is reasonably and compactly laid out as a whole, with a combination of feeding, crushing, drying and discharging. C. The total investment is low and service life is long. 2. A. The temperature of the heat transfer medium can be up to 600 degrees C, and down to 100 degrees C, when discharging. B. The drying thermal efficiency is high compared with other drying system. 3. The feeding quantity is adjustable, with a sealed coal feeder. 4. Measures are adopted to collect the dust, and prevent the smoke at the drying drum, hot blast furnace, and system transfer point. 5. The automatic monitoring system can monitor temperature and pressure at 4 points. The furnace, dryer inlet, and dryer outlet, inlet of induced draft fans, which guarantee the normal and safe production. 6. A big volume drum dryer is adopted to shorten the residence time of coal in the dryer, to prevent coal burning and pulverization. 7. In designing the drum dryer, we consider reliable performance, high capacity, high thermal efficiency, avoidance of caking, etc. In designing a furnace, we consider easy ignition, quick heating, etc. In designing the dust collector, we chose a deducting cyclone, which is high temperature resistant and without moving components, and high efficient pulse bag filter. Thank you for watching, and I hope these courses are helpful to everyone. Subscribing to this channel Cement Industry Courses would be appreciated. Thank you.